Today, we're going to take a journey that starts with something we all know, the laser, and follow its story all the way to a concept that sounds like it's straight out of science fiction, a device that can shoot a beam of pure matter.
So let's just jump right in with a wild question. What if a laser, instead of shooting that familiar beam of light, could shoot a beam of actual matter? I know, it sounds pretty out there, but you're about to see how the groundwork for this incredible idea was actually laid more than 100 years ago.
And it all begins, as so many things in physics do, with Albert Einstein. To really get where we're going with this matter laser, we've got to rewind the clock and look at one of his most brilliant ideas about light.
You know, every single laser you have ever seen, whether it's the little red dot for a presentation or a massive industrial machine that slices through solid steel, every one of them runs on a single powerful concept. And yeah, it came from Einstein all the way back in 1917.
That concept is called stimulated emission, and here's how it works. Imagine you have an atom that's all charged up with extra energy. We'd say it's in an excited state. Now, if a little particle of light, a photon, zips by and hits that atom, something amazing happens. It doesn't just bounce off. It actually coaxes the atom into releasing a second photon that is a perfect, identical twin of the first one.
So you can see how this creates a chain reaction, right? First, you pump a bunch of atoms full of energy. Then, a single photon hits one of them. Pow! Now you've got two identical photons. Those two hit two more excited atoms, and suddenly you have 4, then 8, then 16, you get the idea. This cascade creates a perfectly organized, incredibly focused beam of light. And that, my friends, is a laser.
Okay, so that's how we learned to control light. But our big question was about matter. So is there a matter version of a photon? Well, that question takes us to a really weird place in physics and introduces us to something called the Cooper pair. So way down in the super cold world of superconductors, we're talking temperatures near absolute zero, something happens that shouldn't. Electrons, which have the same negative charge and should repel each other, actually start pairing up. Two electrons link together to form a Cooper pair, and this duo starts moving and acting as if it's a completely new, single particle.
Now here's the absolute key to this whole thing. These Cooper pairs belong to a class of particles called bosons. That might sound like jargon, but all you need to know is that photons are also bosons. And being a boson means you're social. You don't mind sharing the exact same space and quantum state with others. This is why you can stack countless photons into a laser beam. So, if Cooper pairs play by the same rules, could they also be stacked up? Could they undergo stimulated emission? The theory says yes, and that's the breakthrough.
But, just having the right kind of particle isn't enough. For our original laser, we needed an excited atom to release the photons. So what's the equivalent for our matter laser? Well, that brings us to a mind-blowing Nobel Prize-winning discovery, a giant quantum atom. And believe me, this isn't some old, dusty theory. This is cutting-edge stuff. The 2025 Nobel Prize in Physics was actually awarded for the work that made this next step possible, for figuring out how to take the weird rules of the quantum world and blow them up to a scale we can actually see. So what do they actually build? They created a special kind of superconducting circuit. But here's the wild part. The entire circuit acts like a single, massive, artificial atom. It has its own distinct energy levels, just like a real tiny atom, but it's an object that humans designed and built. And when I say massive, I mean it. This quantum object, this man-made atom is, and I'm quoting here, large enough to be seen with the naked eye. Just let that sink in for a second. We're talking about a quantum object, something that is normally fundamentally invisible that is now big enough for you to actually see. All right, let's take stock. We've got Einstein's principle of stimulated emission, we have our special matter particle, the Cooper pair, and now we have a giant artificial atom to emit them. It's time to put all the pieces together and make the leap. So let's look at this side by side. For a normal light laser, the recipe is simple. Your particle is the photon, your emitter is an excited atom, and your output is a beam of coherent light. Okay, now let's build our matter laser. What's the particle? It's the Cooper pair. What's the emitter? It's that Nobel-winning artificial atom circuit. And the output? A coherent matter wave. So, just to recap the ingredients one more time. First up, we need our version of a photon, our matter bullet. And that is the Cooper pair. Check. Next, we need the thing that's going to shoot them out, our giant atom. And that's the incredible superconducting circuit. Got it. But wait, how do we pump it full of energy?
Well, it turns out that's the last piece of the puzzle. We can get this artificial atom into an excited state just by hitting it with precisely tuned microwaves.
And there you have it. With the particle, the emitter, and a way to add energy, the conclusion is just right there. A matter laser isn't just a sci-fi dream anymore. It is conceptually, physically possible thanks to real Nobel-winning science.
So you might be thinking, okay, that's cool, but so what? Why go through all of this trouble? What's the point of creating a beam of matter? Well, that brings us to our final chapter, looking at what this coherent future might hold.
A coherent beam of matter isn't just some lab curiosity. It could change everything. We're talking about the potential to build revolutionary quantum computers. In fact, these artificial atoms are already being used as the basic building blocks, or qubits. This technology could lead to sensors so precise they could measure things we've never been able to detect. It would let us simulate and understand complex quantum systems and truly revolutionize physics research from the ground up.
So I'll just leave you with this final thought. About a century ago, we mastered light. And that gave us lasers, fiber optics, the internet. It completely reshaped human civilization. So the big question we're now facing is, what happens to our world when we finally learn to control matter with that same incredible precision?